Hey guys, today we're doing section 3.6, which is still dealing with exponents. In this section we're going to be comparing two expressions that have exponents in it. But to me, the emphasis really here is still on how good are you at simplifying expressions with exponents. They're easy to compare as long as you know how to simplify them. So let's look at that. It says in this section we will be comparing two exponential expressions to see if they are equivalent or if one is larger. All right? But really, the main thing we are still practicing is simplifying. And we have one new skill here, and that one new skill is rewriting an exponential expression with a different base. So we'll look at that in a minute. Let's start with two equivalent expressions. Equivalent expressions are simply two expressions with the same value. If two expressions have the same value, they're called equivalent expressions, right? Such as 2 times 12 and 20 plus 4. Those would be equivalent expressions. They both equal 24. Or we could have some variables, 5x and 2x plus 3x. Those are equivalent expressions. They both equal 5x. Or x to the 12th and x to the 3rd to the 4th. Again, those are equivalent expressions. And we'll get back to why that's important in just a minute. I guess we're going to do it right now. Write 4 expressions equivalent to 2 to the 20th. So 4 expressions. One might be 2 to the 2nd times 2 to the 18th. Do you know your exponent properties well enough to do this? All right, when you multiply things together, you just add the exponents. That's why those two amounts are equal to each other. Another one that multiplies might be 2 to the 7th times 2 to the 13th. Of course, that uses the same property, so it's not that exciting. Another one might be 2 to the 10th to the 2nd. That uses a different property, right? That uses the power to a power. And another one that might use a power to a power property would be 2 to the 4th to the 5th. So the point is, there are lots of different ways to write equivalent expressions. And that's going to help us here in a minute. We have one do you get it example. You have written equivalent expressions. Can you recognize equivalent expressions? Which expressions are equivalent to 5 to the 8th? Well, maybe we'll just simplify each of these. Again, that's really what we're working on, simplifying, and see which ones are equal. When you multiply stuff together, you add the exponents, so that's 5 to the 9th. That's not equal. When you multiply stuff together, you add the exponents, so that one is equal. When you divide, look at this. They want us to divide the exponents so it'll be equal to 5 to the 8th. But we will not fall for that. We know you subtract the exponents when you're dividing. That would be 5 to the 14th. So that one's not equal. And last up, I have an exponent to another exponent. That's when you multiply the exponents. That would be 5 to the 8th. And that one is equal. Did you get that as well? All right. Here we're just going to practice using our ability to simplify expressions. And once we simplify them, we're going to see which sign belongs between them. Either less than, greater than, or equal to. But I keep reminding you, the important thing here is still how good are you at simplifying expressions? This is really just more practice using the exponent properties, right? So the key here is to, we'll just simplify them. This one is already simplified, but on the right side, when you multiply these together, you would add their exponents, giving you 3 to the 5th. And of course, 3 to the 6th is bigger than 3 to the 5th, so we would do that. In example B, this one is already simplified. Over here, though, I would subtract the exponents when you're dividing. So 8 minus 4 is 4. And it turns out that these two are actually equal to each other. This brings up an interesting one. So this guy is already simplified, but these guys need multiplied together. And when you multiply them, you get 1/4. And of course, when you're multiplying, you add the exponents, so it'd be 1/4 to the 10th. Right? I think they were hoping we'd multiply those and get 16, so it'd be the same. But we didn't fall for that, did we? All right, but here's an important point to make. I'm not sure if you know this, but look. Each time you multiply by a number less than 1, the answer gets smaller. Yeah. Each time you multiply by a fraction, did you realize the number gets smaller? For instance, if I have 1/2 times 1/2, now remember, my original number here is 1/2, and I multiply by that by 1/2, I get 1/4. 1/2 got smaller. And if I multiply it by 1/2 again, that equals 1/8. And again, smaller. Each time I multiply by 1/2, my number gets smaller and smaller. Multiplying by a proper fraction actually makes the number get smaller and smaller and smaller the more times you multiply. Why does that matter? Because here I am multiplying 1/4 to the 16th power. I'm multiplying 1/4 times itself 16 times. And here I'm multiplying 1/4 times itself 10 times. The more times you multiply by a fraction, the smaller the number gets. So to the 16th is actually the smaller amount, right? And then I've got one more here for you. This one's already simplified. Over here, I need to divide, and dividing means subtracting the exponents. So that would be to the 33rd. And of course, that makes this one bigger. 9 to the 12th would be smaller than 9 to the 33rd. All right. Now that we've compared these, we want to be able to compare exponential expressions, possibly, that have different bases. And the way you do that is to rewrite them so they have the same base. This is the new skill in the notes. Rewriting expressions with a different base. The key to rewriting an expression with a new base is recognizing when a number is a perfect square, we'll call that PS, or a perfect cube, we'll call that PC. When a number is a perfect square or perfect cube, it is easy to rewrite it with a different base. I have an example. Because 49 is a perfect square, right? We know 49 is a perfect square. It could be rewritten as 7 to the second power. So instead of 49 to the first power, it's 7 to the second power. Or, because 8 is a perfect cube, it can be written as something cubed, right? In this case, 2 cubed. All right? Now, how does this help us? Well, let's show you. It gets a little trickier here. It gets a little tougher when the original expression is already an exponential expression, right? And you want to write it as a new exponential expression, but with a different base. For example, 9 to the 5th. Now again here, you guys, the key is that the base is a perfect square. 9 is a perfect square, right? And because 9 is a perfect square, I can rewrite it. Since 9 is a perfect square, it can be rewritten as 3 to the second power. Right? So I started with 9 to the 5th, but I'm rewriting the 9 as 3 to the second power. So then the original expression, instead of 9, it would be 3 to the second power. That takes the place of the 9, but it's still to the 5th power. All I did is take the 9 and rewrite it as 3 to the second. The 5 is still on the 9. Then, using my power to a power rule, I can multiply the exponents together, and I get 3 to the 10th power. So I claim 9 to the 5th and 3 to the 10th are equivalent expressions. I just rewrote it so the base was smaller. The base is a 3 instead of a 9. All right, we're going to practice a few of these. All right, so we're going to take the base, which is a perfect square or cube, and we're going to rewrite it. And then we're going to apply the exponent property to rewrite the exponent. Here we go. 4. Is 4 a perfect square or perfect cube? Well, of course, it's a perfect square. So 4 can be rewritten as 2 to the second power. But all I did was rewrite the 4. The exponent needs to stay on there. Then I go ahead and use the power to a power rule, and this would be 2 to the 6th power. All right? How about 25? 25, we all know, is also a perfect square. So let's take the 25 and rewrite it as 5 to the second power. But the 4 is still on there, right? Then I can apply the power to a power rule, and this would actually equal 5 to the 8th power. Let's do a perfect cube. Here I have 8, which is a perfect cube. When something is a perfect square or cube, you can rewrite it. 8 can be rewritten as 2 to the 3rd power. But the 5 that was on the 8 also needs to be on the 2 to the 3rd power. And then you can apply the exponent rule, and that is 2 to the 15th power. And last up, see if you can get this one before I do it. Maybe pause it. On this one, 27 is a perfect cube. It is 3 to the 3rd power. Of course, the 8 would still be on there, which makes this actually equal, the board doesn't like it over there, 3 to the 24th power. All right, I hope you got that one. All right, we are now going to see how that skill helps us. We're now going to compare expressions, unlike before, where we compared expressions that had the same base, right? They both had a base of 7. Now we're going to compare expressions that do not have the same base. But if you rewrite them properly, they will. Here we go. 4 is a perfect square here, right? 4 can be rewritten as 2 to the second power. But that 4 had a 21 on it, so the 2 to the second needs to have a 21 on it. Go ahead and apply your power to a power, and this is actually 2 to the 42nd power, 42nd power. Over here, I am multiplying these two things together. Oh, but wait a minute. They don't have the same base. This guy needs rewritten so it has the same base. And 8 is a perfect cube. I can rewrite this as 2 to the 3rd power to the 4th power. And of course, that would be 2 to the 12th power. Now we bring down our other one, 2 to the 28th power, and we multiply these guys together. And when you multiply them together, you add their exponents, gives us 2 to the 40th power. So you can see now these guys are written. These guys are written so that they have the same base. And obviously, which one's bigger? Well, 2 to the 42nd is bigger than 2 to the 40th. Let's try that one more time. Maybe see if you can get it before I do it. All right, 3 to the 4th power cannot be rewritten because 3 is not a perfect square or a perfect cube. But over here, I have a division problem. Now, I can't actually divide them because they're different bases, 9 and 27. But I think they can be rewritten with the same base. All right? Start with 9. 9 is a perfect square. So I can take 9 and rewrite it as 3 squared to the 8th power, which would actually equal 3 to the 16th power over the 27. 27 is actually a perfect cube, so it can be rewritten as 3 to the 3rd power. But of course, it was to the 5th power. And then when you do your power to a power, 3 times 5 gives you 3 to the 15th. And finally, we can now take this fraction where they do have the same base, and we can divide. And when you divide these, you of course subtract the exponents. This would be 3 to the 1st power. So now it's obvious which one's bigger. 3 to the 4th is bigger than 3 to the 1st, and I would have that. All right, good luck on the homework. See you soon.